Now this is our next question. B, right? So the B. Now we are being asked to find the determinant, right, of 3a b to the negative 2 c squared, right? Now we will actually be moving fast because I've done what I had to do earlier. So we will actually be moving fast. Now, there is a formula, right, that you have to know before you'll be able to solve this question. Okay, and the formula is that the determinant of km, right, is equal to k to the power n times the determinant of m. Now, I would like you to write this formula down, right, where n um is the number of the rows or columns, okay, because this actually applies to 2 by 2 matrices or 3 by 3 matrices, okay. So in that case, n is 3 in this instance. So let me come back again. When we go to our question, the question says that if the matrix A, B, and C is a 3 by 3 matrix, right? Then find AB. So that's the question. Okay. Now the K here is a constant, where in this case 3, okay. And N here is our matrix. And the N over here is the number of rows or columns. Okay. Where N, right, is the number of rows or columns of the square matrix. Okay. Now, so let's so from our first question, right, we got that the determinant of AB is equal to the determinant of A times the determinant of B. Therefore, we can separate all these ones as the determinant of 3A, right, times the determinant of B to the negative 2 times the determinant of C squared. Please hope you are following. Now, for the 3A, we are going to use this formula. Okay. So now, this is equal to this is equal to 3, right? 3 is our constant, which is in this case 3. So 3 is our constant. Now, what is our n? The question says that A is a 3 by 3 matrix, right? So our n is 3, right? This formula is actually used for square matrices, and in every question that you will be given, it's either a 3 by 3 or a 2 by 2. Okay, for 1 to 6. So in this case, we've been told that A, B, and C are 3 by 3 matrices. Okay, so n is actually 3, so we get 3 cubed. Okay, times the determinant of m. So in this case, the determinant of A, which is 2, times the determinant of B to the power negative 2. Now this is not a big deal. We just take the determinant of B, right, which is 3, and raise it to the negative 2 power. Okay, and similarly 5 to the power 2. Am I communicating? So now we obtain 27, right, times 2 times 109 times 25. So we can simplify this as 2, sorry, 1, right, and 9 goes into 27 three times. Then we end up getting 75. I think there's something wrong with my calculation somewhere. Let me, 1 minute please, let me check it out. Let me check it out. Yeah, I think this correct. So 75. Okay. Please hope you all get me. Hope this clear, please. So with the negative here, we just invert it. We just invert the we just raise the determinant to the power negative 2 and just invert it and square. Okay. So this is what we get for this question. So now with the C, right? The C is actually very simple. The determinant of A squared C transpose B to the power negative 1, and this is equal to the determinant of A squared, which is 4. The determinants of a matrix, right, and its transpose are the same. Okay. So the determinant of C transpose is the same as the determinant of C. which gives us 5. And similarly, b to the negative 1 gives us 5, 1 on 5, right? This cancels out. Sorry. The determinant of c is, the determinant of b is 3, right? B is 3. So we get 4 to the power, 4 times 5 times 1 on 3. Okay, so we obtain 20 on 3. So hope we all get this. Sorry, I was a bit shaky. I'm trying to set up my tools and some logistics. So um, I'm actually having divided attention, but I think it's okay now. So now let's move on to our next question. So as I said, if you just join us, I've sent the questions we are solving to the group. Okay. Prince, your hand is up. Please, do you have any questions? Prince, Prince, any question? So if you have any question, you can just unmute and speak. Okay.
Yeah.
Yeah, Prince.
With the B, the answer I got was 150.
150, 159,
Yes.
right?
It was no the it was 27 times 2 times 1 over 9 times 25.
Yes.
And if you cancel out, nine will go in 27 three times. So 3
Yeah.
times 2 will give you 6.
Okay. All right.
And 6 times
Yeah.
25 is giving us.
All right. Thank you very much. Thank you very much. Yeah. So you are right. 625 gives us 150. Thank you very much. So hope it's clear now, please. Thank you very much, Prince, for the correction. So now we would be moving to our next question. Okay. And the B. As I said, the B is actually the IA2 of 2023. Okay. So if you have solved it, that's quite great. Okay. But if you haven't, let's do so right now. So if E is a 2 by 2 matrix, right? Sorry. If E is a 2 by 2 matrix, let me clear this. Now, E is a 2 by 2 matrix, and the trace of E is 0, right? Then E square is equal to lambda I square for some scalar lambda. Okay, for some scalar lambda. Now we are being asked to find this lambda. Now remember what we said trace was. So when we were going to trace transpose minus cofactors and adjoints, right? As I said, you will not often be given a direct question that find the minus of this matrix, find the trace of this matrix, right? But you apply this concept that you've learned, right, in some word problems or any application questions, okay? And this is a clear example. We've been given E, right? And E is a 2 by 2 matrix. This is very important. You can't just start without knowing what type of matrix you've been given. So E is a 2 by 2 matrix. So let's represent E by the entries, and let's take A, B, C, and D. You can also represent the entries A11, A12, A21, A22, where the first number, right, is the row number and the second is the column number. But I just figured out that this is actually quite simple and less complicated because the the different letters are actually quite clear to see. Okay. Now what did we say the transpose? What did we say the trace is? The trace is, right? So now we said the trace is the sum of the entries of the major diagonal. That's what we said the trace was. So in this case, the trace of E, right, is equal to A plus D. And the question says that the trace of E is 0. So this is the first equation. The trace of E is 0. Now, we are told that E squared, right, is equal to lambda times our identity matrix. Okay. So now let's find A squared. But before we even continue, right, we can do something, right? A plus D is equal to 0. So we can make A the subject. So A is equal to negative D, or D is equal to negative A, right? So now let's replace D with negative A. So E is now equal to A, B, right? C, negative A, right? So now E squared gives us A, B, right? C, negative A. Please hope you all get it up to this point. So as I was saying, the trace is actually the sum of the entries of the major diagonal. Okay, the sum of the entries of the major diagonal. So continuing our multiplication, we get again A, B, C, negative A, right? And this is equal to lambda, right? Hence our identity matrix I2. Okay. So now, cross multiplying, we obtain E squared is equal to horizontal times vertical, right? So we get A squared plus BC. Okay. So we get A squared plus BC. This times this, we get AB, right? AB minus AB, right? Horizontal times vertical, right? So again, we get AC minus AC, right? And finally, horizontal times the vertical. Okay. So we get BC, right? BC, right? Plus A squared, right? It's equal to lambda I2. Okay. Now, how can we simplify this? Now, this and this cancel out. Okay. This and this cancel out, leaving us with A squared plus BC. Okay. 0, 0. A squared plus BC. Okay. And this is equal to lambda I squared. Now from this is clear, right? The lambda is equal to what? A squared plus BC. Okay, and we are done. So this question we just solved was actually the IA2 of the 2023 EF group. Okay. So let's move on to our next question. I would like us to finish quickly and start with the and start with the complex numbers. Hello, please. Do you have any question? Do you have any question? Right. So now with this one, we will not be solving. We'll just like how should I put it? We just solve with me, okay? Now, suppose that the determinant of this matrix, right, is equal to 4. Compute the determinants of the following matrices. Okay, compute the determinants of the following matrices. So just take 1 minute to go over this, then we just solve it after the next minute. Remember, I said there are certain rules governing the operations of matrix, cofactors, and traces, transpose, and the rest. Okay, it's quite important for you to go through them and become get like abreast with them. Okay, it's very important. Okay, so let's start. Now, looking at the A, right? The A is similar to the original matrix we've been given, but the only difference is that the first and the last row have been swapped, right? The first and the last row have been swapped, and by the laws of determinants, right? By the laws of determinants, we say that wherever, right, you swap two rows, right, the determinant is of the swap row is actually negative the determinant of the original, right? So the determinant of A, right, is actually equal to -4. Then you are done. Why? Because when we swap a row, right? So in this case, we are swapping the third row and the first row, right? So because of this swap, right, the determinant of the original matrix is actually the negative of the other, right? So when you just swap a row or a column, you just negate the matrix. Okay, it's not only rows, okay, columns also. So if I swap this ADG, right, with CFI, right, for us to get the determinant of the swap row, we just have to negate the determinant of the original matrix. Hope that's clear. Now let's go to the B. Now the entries of the second row and the third row have been multiplied by a constant. And in the second row, the second row has been multiplied by 2, and the third row has been multiplied by 3. Okay, hope that's clear. Now, again, by the laws of determinants, let me put it that way. Um, Whenever you multiply a column or a row, please take note. In all the examples you are solving, it's quite unfortunate that okay, not quite okay. I think we have one example that actually use the row something. So yeah, so we'll be coming to that one. So now, back to the question B. The second row was multiplied by 2, the third row was multiplied by 3. So to get the determinant of the B, we actually multiply the determinant of our original matrix by 2 and also by 3. Okay, if you join our previous in-person sections, we actually saw how matrices were obtained, right? And we said that it's due to certain computations with the computer, right? It's easier to do so with matrices. And that matrices actually can be are actually equations, right? That have been represented in simple forms as a table, right? Okay. So now when you're having an equation, right, and you multiply your equation with a constant, you see that um, um you can get your original equation back by just dividing both sides of your equation by the constant. Okay. So you are not changing any question. Like please do get the point. Yes. So when you multiply both of your equations by both of your rows by a constant, as I said, you multiply your determinant of the original matrix by the constant. So now the determinant of the B would actually be 4 times 2 times 3. Okay. So 4 times 2 gives us 8, and 8 times 3 gives us 24. So B is equal to 24. Now let's take the C. Now the C, two things have been done to the rows, to the columns of C, right? In the second column, we can see clearly that the column of A was added to the column of B, and the third column was multiplied by a constant 2. Again, going back to the rows, right? When we add two rows or two columns together, right, the determinant is maintained. So the fact that we've added the column 1 to the column 2, right, doesn't affect our matrix. Okay. Now, for the multiplication of the constant by in the third column, right, our determinant is affected. So we get a determinant of 8. Okay, hope that's clear. Yes, so we are done with that one. And let's look at the question 4. I think the question 4 also
Now,
deal with
please, can you
similar
go for the
determinants.
C?
The C. Alright, alright, alright. So now what I was saying for the C is that now for the C, two things have been done to the C. Okay. The first is that um the second column, right, has been the first column has been added to the second column to obtain the second column. Do you get it? And for the third column, we have to multiply all the entries. Okay. Now for from the rules of determinants, right? We got that adding one column or one row, right, to another column or to another row, like column to column, row to row, right, doesn't change the value of our determinant. Okay. Now, for the second column, right, we've got a constant to multiply the second column. Okay. So now the determinant of the matrix C, right, is only affected by the operations that have been done in the third column. Okay, because adding one row or one column to a row or a column doesn't affect the matrix, as you said earlier. So the operation on the second column, right, doesn't affect the determinant of our matrix. Okay, so now the matrix of C, the determinant of C actually becomes 4 times 2. Please, hope that's clear.
Yeah, it's fine.
Alright. So now let's move on to the question 4, right? The question 4. Now these questions are actually aren't really don't really involve a lot of steps. Okay, so we are just solving them quickly. So, but this one will be going back to the blackboard. The matrix A is equal to 0, 1, -1, 0. Right? Calculate A to the power 1000. And this one, when you start by doing A1, A2, A3, we are going to spend 2 years solving one question which you might probably get it wrong, okay, because of errors. And there's actually a simple way to do that. Now, with questions like this, okay, all you have to do is to just attempt, okay. And when you try attempting it, you see that it becomes clearer, okay. Now, let's see what I mean by you have to attempt, okay. Now, let's go back to our blackboard. Let's go to our blackboard. Let me clear this. Let me clear this. Now, we have so I'm recording, okay. So after I'll share the video with you, okay. It's quite big. That's why I haven't shared the previous ones, already, but I'll try and do so tomorrow. Okay, but please focus in case I'm not able to send, then you just get it from here. So the matrix A, right? The matrix A is equal to 0, 1, negative 1, 0, right? And I've been asked to compute A to the power 1000. Okay. So does anyone have an idea? Feel free. Like anyone with an idea. Okay. So now let's start. So the first thing we have come to do is to compute A to the power A squared. Okay. So A squared is A multiplied by A, right? The matrix A multiplied by the matrix A. Okay. And this gives us negative 1, right? 0, 0, and negative 1. Okay. I want us to move fast. That's why I'm just computing this quickly. Okay. So 0, 1 multiplied by 0, 0, 0 gives us 0. 1, negative 1 gives us negative 1, right? This times this. 0 times 1, 1 times 0. Again, 0 times 1, 1 times 0 times negative 1. Okay. So in that order. So this is A squared, right? This is A squared. Okay. And you can do it and compute for A3, right? A3 is actually this matrix that we've gotten negative 1, 0, 0, negative 1, right? Times A, right? Negative 1, 0. And this gives us um, 0, 1, negative 1, and 0. Okay. So negative 1 times 0 gives us 0. 0 times negative 1 gives us 0, right? Negative 1, again, this row times this column. Negative 1 times negative 1. Negative 1 times negative 1 gives us negative 1. Sorry, negative 1. Well, let me check something right now. This so no, I think we've done a mistake. I've done a mistake in the computation. So negative 1 times um 0 gives us 0. Yeah, this gives us 0. But this part, this supposed to be, oh no, I'm doing the same mistake twice. Let's go over it again. Okay. So negative 1, right? This row times this column. Okay. So we get 1, 0, 0, 1. Oh no, we don't get this. I'm so sorry. I've solved it already and I want to move fast. That's why it's like I'm trying to do it this way. Okay. So negative 1, right? And negative 1 times 0 gives us 0, right? 0 times negative 1 gives us 0. 0 times negative 1 times 1 gives us 1. 0 times 0 gives us 0, right? So now 0 times 0 gives us 0. Negative 1 times negative 1 gives us 1. 0 times 0 times 1 gives us 1. Sorry, 0 times 1 gives us 0. Negative 1 times 0 gives us 0, right? So finally, A4, right? We could actually do this the easier way by computing for A squared, right? And multiplying them together, okay? But this method is also equally correct. Negative 1, 0. right? Now, 0 times 0 gives us 0. Negative 1 times negative 1 gives us 1, right? Now, 0 times 1, negative 1 times 0 gives us 0, right? 0 times 1 times 0 gives us 0. 0 times negative 1 gives us 0. And finally, 1 times 1 gives us 1. 0 times 0 gives us 0, right? So 1 and 1 plus 0. So this gives us 1. So, right. So now a to the power 4. Please, are you seeing where we are getting to now? Gives us an identity matrix, right? A 2 by 2 identity matrix. Okay. Now, any number you multiplied by an identity matrix, right? You get back that number. Okay. Now, take note of something. A to the power 1000, which we've been asked to find, right, is equal to a to the power 4, right, times 250. Please, do we get this? And since a to the power 4, right, is an identity matrix, right, multiplying a to the power 4 by itself multiple times, right, still gives us a to the power 4, right, which is still this identity matrix. So a to the power 1000 is also equal to 10, right, 01. Please hope this is clear. Please, do we all get this? Sorry for the pauses in the question bar. Please, do we get this? Do we get this, please? Hope it's clear. Hello, is it clear, please?
Yeah, it's fine.
Alright. So now let's move to the next one. I think we've done everything in the. Okay, I think we are done for today with respects to the tutorial section. Now the next thing that we are doing is the model 2. Okay, and as I said earlier, right, I'll be taking you through the arguments and the principal arguments. Okay, that concept is very important to me, and I think we have to go over it one more time. So if you weren't in class yesterday, okay, this is a good time to really get what the argument is and what the principal argument is. Okay, now yesterday we made a very important relation. Okay, we made a very important relation, and we said that. Okay, no, before we do that, okay, let's still continue. We made a very important relation. I wanted to pause because yesterday I promised to take you through the second method uh, um, of proving that a relation, right, is linear, right. With the second method, we actually solved for one method, right, and I promised that we won't be looking at the second one today. But let's try and do this. Then after, when we have time, we'll continue with that one. If not, we'll continue tomorrow in class. Okay. So now we made a very important relation yesterday, and we said that arc right arg is equal to a principal argument, right, plus 2n pi, right, where n is an integer. This was the relation that we made in class, right? So just take 1 minute and just look at this. Please try and get this because often people confuse what the argument is and also what the principal argument is. Okay. So please try and get this. Try and get this. The small argument is actually your angle that you solve, like when you are given any question. Okay, and the argument actually is the angle that falls within this interval. So negative pi, right, less than or equal to theta less than or equal to pi. Okay, so right, once your angle falls between this interval, right, it falls in the interval, right, then you have a principal argument. Okay, so when you are given a question and you solve for your angle, right, and you get an angle that falls in that interval. You don't have to convert this to a principal arguments to or arguments to principal arguments. No, an argument is a principal argument if it falls in that interval. Okay. So hope that's clear, please. I really want everyone to get this concept. It's very important to me because we would be using the principal argument to solve a lot of questions down there. Okay. So now let's move on. Come in 1 second, please. I want to get a question. Okay. So I think we can continue now. So yesterday in class we actually saw one question. Okay. We actually saw one question. And let me try and open the slide so that we actually use the slide alone. Okay. So these are complex numbers. Okay. And we were on this slide. Okay. This was the example I was looking for, right? Negative 3i, right? Minus negative root 3, right? Minus I, right? And the principal argument has actually been gotten, okay? And actually, this when you just look at this, it doesn't make sense, okay? It doesn't make sense. I don't know if there are so many ways to find the principal arguments, right? But often, right, it doesn't make sense because what's here in this example here, right? Because it was in this quadrant, right? It was subtracted, pi was subtracted from it, okay? Pi was subtracted from it. But someone too asked, but pi on 6 falls in the interval negative pi, right? Less than or equal to theta, less than or equal to pi. So why do you have to subtract pi from it? Okay. And the reason why they did that because there's actually a formula for what they did, okay. And the formula was actually being followed in that situation. But I want to teach you how to get the principal arguments right from a theoretical point of view. Okay. So let's go. So we were given negative root 3, right? Negative root 3 minus I, right? And we have to find the principal arguments from this. Now, drawing our number line, right? Drawing our number line. The principal argument actually falls in this interval, right? And the negative x is negative over here, y is also negative, right? So it falls somewhere here, right? Now, when we punch this on the calculator, okay, when we punch this on the calculator, right, we get 30 degrees, okay, 30 degrees, right? Now, the angle that we are actually considering over here is actually the entire angle over here, okay? So 90 plus 90 plus 30, right? And we get 210, 210. Now, changing to radians, right, we multiply by 180 on pi. We solve that clear because after we've gotten the angle, right, we change to radians, okay, by multiplying this by 180 on pi. And with this, we get what? Sorry, pi on 180, okay. And with this, we get 7 on 6 pi, okay. Now, this is clear that 7 on 6 pi doesn't lie in this interval, okay. 7 on 6 pi doesn't lie in this interval. So there is, so this is our argument, right? And there is a need for us to convert our argument into our principal argument. Okay. You can also rewrite this formula as argument, right? Is equal to the small argument, right? Minus 2 and 2 pi n. Okay. So now when you have your argument, right, and you subtract multiples of 2 pi from it, you end up getting your principal argument. Okay. Now from the example that we saw in the lecture notes, pi was subtracted from pi on 6, which actually falls in that interval. Okay. and it's actually quite confusing when to know whether to subtract by 2 pi, when to maintain it, or when to. So solving it from a theoretical point of view is actually always the best option. Okay, because as we solved yesterday in class, it's not every question that you can actually use. You can actually use the formula for. Okay, so now this doesn't fall in this interval, so we are going to subtract multiples of 2 pi from it. Okay, so 7 on 6 pi minus 2 pi, right? And this gives us negative 5 on 6 pi. So this is the actual answer that we should get when we do that subtraction. Okay. So now let me go over this again. This was the this was the values we are given, negative root 3 minus I, right? And we know that this falls in the third quadrant, okay, the third quadrant, okay, where both I and x and y are negative, and in this case, the y represents the imaginary axis, okay. Now, the angle over here we calculated by using the formula tan theta, right, is equal to y on x, right. So we found tan inverse of both sides, right. So theta is equal to tan inverse of y on x. That's what we did. We did this yesterday in class. That's why I don't want to mention it. Okay. So theta is equal to tan inverse of y on x. Okay. So in this case, ry is r negative one, right? And rx is root 3. Okay. So now solving this, we get theta is equal to 30 degrees. Okay. And we said that the angle we use in this case, right, is actually everything here, right? Everything here from this point, okay? Everything here is considered, okay? So we add 90 to 90, which gives us 180, and 180 plus 30, which gives us 210, okay? So converting to radians, right? We multiply by pi on 180, and this gives us what 7 on 6 pi, okay? And this is our argument. Why? Because it doesn't fall the um in the interval we've been given, pi less than or equal to theta less than or equal to pi. So we subtract multiples of 2 pi from it until we get a number that falls in that interval. Okay. So now subtracting our first multiple 2 pi, we get negative 5 pi on 6. And negative 5 pi on 6 actually falls in this interval. Okay. Forgetting about your pi, you get negative 1 less than or equal to theta less than or equal to 1. Okay. And with this, we get negative 5 on 6, which gives us something like 0.833 something. Okay, so negative 0.8333 recurrent. I think that's the value we should get. Falls in this interval, right? Negative 1 to 1. Okay, so that's how we obtain our principal argument in this case. So we are going to take one more example. Okay, one more example. Then we move on. Now, so z is equal to, let's say z is equal to I. Okay, z is equal to I. Now, what is the principal argument? We solved this yesterday in class, but I figured the explanation wasn't clear enough. Okay, so let me explain this again. Now, for the example we did, right, we saw that the the points, right, plotting the points, right, was somewhere here, right. So we actually just drew a line, approximated that like the points would be here. So we just drew the point, the line from the origin, right, to pass through this point. Okay. Now with this, let's actually try and do so. Now the this is a complex number, right, and it's made up of two parts, right, the real and the imaginary. Now our real part is 0, and our imaginary part is 1, right. Now this means that the real part, which is on the x-axis, right, is 0, so it's at this point, and the imaginary part is 1, which is on the y-axis. So we get something like this. Okay. Now as I said earlier, we take angles with respect to the horizontal axis. Okay, with respect to the x-axis. So in this case, we had this angle over here, right? Um, we don't take this one because this one is um, this one is directly we can just map this side of the angle to the horizontal axis. Okay, once we can't do this without crossing this barrier. Okay, so now the angle we solve is actually this part. Okay, now the same thing also applies for this one. Okay, we actually solve it with respect to the horizontal axis. Okay, the horizontal axis. So now drawing the angle here, right? Drawing the angle here, right? From here to meet the horizontal axis, we obtain this 90 degrees, which is pi on 2. Okay, that's why we had pi on 2. Okay, now pi on 2 actually falls in the interval negative pi, right? Less than or equal to x, less than or equal to pi. Okay, and that explains why this is the principal argument. Okay, and this also the argument. So now that explains the how to get the arguments from the principal arguments. Okay, they are formulas and the formulas are actually somehow confusing, and it's not always that you can use the formula tan theta is equal to um pi on x, right? And theta is what's on x, because in some situations where okay in a situation like this, right, you get tan theta, right, is equal to what 1, right, 1 on 0, and this is undefined. Okay, so it's not always that the formula holds. That's why it's quite important to know how to get it right graphically. Okay, and that method always works. Now there's one thing that we are coming to look at. We are coming to look at where we've gotten to now. I think the calculations that we would be doing are somehow quite lengthy. Okay, so we would be doing a lot of the lengthy ones tomorrow in class. So please make it a point to come early for tomorrow's section. Okay. So now there's a theorem that I would like us to go through. Okay. Now, it's not really a theorem, but it's just some formulas and some relations. So, um, the polar form of complex numbers. Okay, that's what we are coming to do right now. The polar form of complex numbers. Now, what do we mean by the polar form of complex numbers? The one hour. The polar form of a complex number is given by the form z is equal to r, right, cos theta plus I sin theta. Okay, so we all know this. Okay, this is the polar form of the complex number. So now, given a complex number, negative root 3, right, minus I, right, how can we represent this in the polar form? Now, this represents the modulus. The R here, right, represents the modulus, right, and the theta, right, represents the argument. Okay, we already know this. Now, the theta that we will be using in this case is actually the principal argument. Okay. So now let's find the modulus. Okay. So r is equal to the square root of x squared plus y squared. Okay. And this gives us the square root of the root of 3 squared, which gives us 3 plus 1 squared, which gives us 1. Now the square root of 4 gives us 2. Okay, with all what's in this. Now let's find for our principal argument. So again, let's do this graphically, which I recommend. So now this complex number falls in this quadrant, right? In this quadrant. Now the tan inverse of 1 on root 3 gives us 30 degrees. Adding these two angles, right? We get 210 on 180, right? We get 210, right? And converting to radians, we multiply by pi on 180, right? And this gives us 7 on 6 pi. Okay. Now, this is the argument. It doesn't fall in the range negative pi less than or equal to x less than or equal to pi. Okay. So we have to subtract some multiples of 2 and pi from it, right? Multiples of 2 pi from it until the angle falls in the interval negative pi less than or equal to x less than pi. Okay, so subtracting negative 2 pi from this, we obtain negative 5 on 6 pi, which is of course in the interval. Hence, our principal argument, our capital arc, right, is equal to negative 5 pi on 6. Hope that's clear. Yes. So now for this equation, right, the polar form of the complex number negative root 3 minus I is equal to R modulus, which is the R, right? We solve for the R as 2, which is the same as R magnitude, right? With respect to the x and y coordinates. Okay. So now times cos negative 5 on 6 pi, right? Plus I sine negative 5 pi on 6. Okay. Now, um, we all know that cos, right, is an even function. Okay. Therefore, cos swallows the negative, right? In layman terms. Okay. So we get 5 on 6 pi, right? And sine is an odd function, right? So what's an odd function? An odd function is a function that when we have f of negative x, right? This is equal to negative f of x, right? So this is an odd function, okay? Whereas an even function, f of negative x gives us f of x, okay? This makes sense. Okay. Now sine is an odd function, therefore f of negative x, and this x in this case is 5 pi on 6. So we get negative I sine 5 on 6 pi. If you are confused whether cos or sine is odd or even, you can just leave it in this case, okay? Probably you lose one or two marks, but it's better than losing everything. Okay, so this is the polar form of complex numbers. Okay, it's represented by this formula over here. And the first thing we have to do is to find our modulus, right, which is the magnitude, and also find our principal argument. Okay, this our principal argument. Now, to find our principal argument, right, we use the formula tan theta on tan theta is equal to y on x, right? Opposite over opposite over adjacent, right? And this gives us r30 here. We take the angle with respect to both of these um um what do we call this thing, quadrants, right? And we get 210. We change two um radians. We get 7 pi on 6. We convert to the principal arguments, right? By subtracting multiples of 2 pi from it. Okay. So the first subtraction gives us negative 5 pi on 6, which is of course in this interval, right? Therefore, we don't need to carry on with further subtractions. Okay, we just maintain it that way. We put this into our original equation, and voila, we have the polar form of the complex numbers. Now, the second thing we are coming to do actually, I would like you to pay particular attention because this was actually last year's IE. Oh no, this was actually last year's IE, and they were actually asked to prove. And one thing about these proofs is that the question can say find show that z is equal to this, and hence okay. So they sometimes bring hence, and of course whenever you see hence, you have to use the solution in the A, right, to solve for B. Hope I'm clear. So please pay attention to this part that we are coming to do. I'm still searching for the IE2 for last year's batch. Then when I get it, I'll send it to the group. I still haven't gotten it. But please, if you have it, you can please send it to me. I'll be very grateful. Now, having these two complex numbers in the polar form, we have Z1, right? Okay, let me use the blue. So we have Z1, right? Now Z1, right, as you saw earlier, has the form the modulus, right, multiplied by cos theta plus I sine theta. Okay. And Z2, of course, is equal to R2, the modulus, multiplying cos theta plus I sin theta. Okay, now Z1, Z2, right, gives us what? R1 multiplying cos theta plus I sin theta, right, times R2 multiplying cos theta plus I sin theta. Okay. Now we are coming to do some basic trick over here. But first, let's factorize our R. Okay. So Z1 Z2 is equal to R1 R2 multiplying the angles cos theta plus I sin theta. Okay. And again cos theta plus I sin theta. Okay. So cross multiplying, we get Z1 Z2 is equal to R1 R2, right? And cos multiplies cos, right? And this gives us there's actually, oh, we didn't define our angles. Okay, so this and this is two. Okay, because they have different angles. Okay, so it's important to actually label our angles. Okay, very very important. All right, now cos theta 1, right, times cos theta 2, this gives us cos theta 1 cos theta 2, right? So again we get cos theta 1 times cos theta 1 times cos theta 1 times I sin theta 2. Okay, now we get cos theta 1 times I sin theta 2, right? So we can bring our I over here and multiply this by sin theta 2. Okay, plus I sin theta cos theta, right? And finally we have plus. So now we have I times I, right? And I squared is actually equal to negative 1. Okay, so we get minus, right, sine theta 1 sine theta 2. Hope this clear. Now we are going to do some quick trick over here. Okay, some trigonometry over here. Okay, now take note of this two, right? This two. Okay, take note of this two, and also take note of this two. Now we can actually factorize this out. Okay, so now let's do something. Now this is actually the formula. So z1 z2, right, it's equals r1 r2 multiplying what? So this is actually the formula. Um, we have the cos theta, right? Cos theta 1 plus theta 2. Okay, right? We all get up to this point, right? Plus now we factorize out our I. Okay, we factor out our I and we get I, right? And we get this is actually equal to, so there is 1 2, right? And this is actually the same as sine, right? Sine let's see, theta 1, right, plus theta 2. Okay, look closer bracket. And this gives us the relation R1, sorry, Z1, Z2. So wherever we are given two complex numbers, okay, which are in the polar form, the first thing we have to do, right, is to multiply their um, modulos together, right? Then after we add their corresponding angles, right? So the argument of cos, the angle of cos adds to the angle of the cos in the other expression. Okay, and we do the same for the sine also. Okay, so hope that's clear. Okay, So this is actually the proof. Okay, so you can be given this and asked to prove it. It's quite simple. Okay, and as I said, this was last year's IE2. They were actually asked to get this expression, right? And they were given a question and they were asked to use the expression they obtained to solve for that. Okay, now we can actually solve Z1 on Z2, right? And when we do this, we are going to get um R1 on R2, right? Multiplying the bigger bracket, cos theta 1 plus theta 2, right? Plus I sine theta 1, right? I'm sorry, this is a negative, right? Minus theta 2, okay. So this is what we obtain when we do Z1 on Z2, okay. So hope this clear. Now I will not be solving the second one I just showed, okay. So please you can try it out and we move on from there, okay. And that's quite important. So please do the try and get the expression I just got, okay, from Z1 and Z2, okay. It's very important. Now I think there are just two more things I would like us to do, okay. So for tomorrow's section, this is what we would be doing. We would be going through the De Moivre's theorem, okay, De Moivre's theorem, and I would like us to do that one in class, okay. And that's actually almost everything, almost all of the model two, okay. Then we actually come and do one or two things, the cube roots of unity. Then we are actually done with the model two, okay. So we would be finishing the model two, God willing, in tomorrow's class, okay, and be solving a lot of examples, okay. But tomorrow we'll definitely be finishing the model two, so please make it a point to come to class early. All right. So now there's one thing that I would like us to do. There's one thing I would like us to do, and yes, we have enough time. So, and that is the proof that an expression that we've been given, and sorry, a transformation that we've been given, right, is linear, right? A linear transformation. How can we show that? And yesterday we saw one method, okay. We saw one method of showing that a transformation is linear, okay. And we saw that we could use the formula LU plus V, right, which is equal to LU plus LV, right? And we saw that if this expression is equal to this expression, right, then the transformation is linear, right? Otherwise, it is not a linear transformation. Okay. Now we would be using another method to show that the a transformation is linear, right? So any of the two methods hold. Okay. So whenever you are given a question, you can use one method. If you have time, you can use the second one. Just try and confirm your answer. Okay, this is very important. So the second formula is L, right, which is Ku, and this is a linear transformation. If LKu is actually equal to KLu, right? So this is the second formula, right? Very, very, very important. Okay, so this is the second formula, the formula that we would be using. Okay. Now we are coming to solve the same questions we solved in yesterday's class, right? Using the method one, okay. Using the first method, okay. Using the second method, we are coming to solve the same questions. Now, before we solve, I want to say that this R square here shows that U and V, right, are actually in two dimensions, okay. So therefore, we also have to state that for the K and U, okay. So U is still in two dimensions, and K, the constant, is actually in one dimension. Okay, so the square comes over here to symbolize that U is in two dimensions. This is actually very important. Okay, now this is the same as KU1, comma KU2, and this is equal to KLU1, right, comma U2. Okay, Hope this clear. Now with both of these formulas, as we did in yesterday's class, right? This is actually in two dimension, as I was saying earlier, right? So you have to rewrite this in two dimension before you be able to apply the formula. Sorry, before you're able to apply the transformation that you've been given. Okay. So this formula is actually given in two dimension. Okay, but before you be able to use this, you have to change it to two dimension. Okay, hope that's clear. Now let's pick one example and hopefully this makes it clearer. Now we have the question txy, right? Txy. Okay, txy. Now, with this txy, as you can see here, this txy is given in two dimensions, right? We have the x and the y components. Okay. Now, just looking at this formula, right? Sometimes looking at this or even this, you can be confused that we've been given x comma y, and this is just ku, right? So once you know that you have to change this to or this to a two dimension, or if you are going for this method, this to a two dimension, it actually becomes quite clearer. Okay. Now we've been given t x y, right? Is equal to 1 plus x, right? Comma 2 plus y. Okay. This is what we've actually been given. Okay. Now we are using this method. Okay. This method. Okay. So now let's write it in terms of, so we can say let's use t um we can use t. Okay, let's use tku, right? Tku should be equal to ktu for the system, for the transformation to be linear. Okay, so you just continue. Okay, because of time, I'm skipping that part. So this is actually equal to tku, comma ku1, right? Comma ku2. Okay, now applying this transformation that we've been given, right? This actually gives us um, this actually results in. So now we can see that x was taken and one was added to it, right? So we take our first thing here. We take our first thing here and we add one to it. So ku1. Okay. Again, we take two and add it to our second term. So 2 plus ku2. Okay. Hope this clear. Now we've found tku, right? Now let's find for ktu. Okay. So now this is for this is for tku, right? tku, right? So now we are coming to find kt. Okay, u. Okay. Now to find ktu, we have to find tu first. Okay. So now tu is equal to this in two dimension u1 comma u2, right? Now this is actually equal to, we take the first term, right? Add one to it. Okay. So we have u1 plus one, right? u2 plus two. Okay. Now we multiply. So then ktu, right, would be equal to ku1 plus k, right? Because k multiplied by 1 gives us k, comma ku2 plus k plus 2k. Okay. And we can see that this expression over here is not equal to this expression over here. Okay. Therefore, this transformation is not linear. Now, this question is actually in the slide, and this first method was actually used. Okay. So this second method also shows that this transformation is not linear, it's not a linear transformation. Okay, so now let's take one more example. Okay, then we'll call it a day. Then tomorrow we'll continue with the De Moivre's theorem. Okay, we'll continue with the De Moivre's theorem. Okay, all right. Now, so we are going to take the second example, the second example. So we've been given the linear transformation. Let's see. Okay, t, right, u1 u2, right, and this is equal to v1 minus v2, right, v1 plus b2, right? And we said earlier that everything we are seeing over here is actually variable. Right? T is a variable. So the previous example that we saw, we actually used L, right? We saw in another case where we use X and Y. Okay. So you can also define yours as, okay, let L be the linear transformation defined on, let's say let's say let's use X. Okay. So for this to be linear, right? For this to be a linear transformation, then this LKU, right, should be equal to KLU, right? Makes sense, right? Yes, makes sense. Okay. So this should be equal. Now let's find for LKU, right? LKU. Now LKU in two dimensions becomes LK1, right? Comma LK2. Okay. And this using the formula we get the first term subtracted by the second term. So now you can see that whenever we are applying the formula for the transformation, right, we don't bring the t in this case, right? Because the t here represents that these two variables, right, are being transformed. So once you bring in another t here, then you are trying to say that we have to transform this again, right? So now once you apply this formula to our expression, we don't actually have to bring RL here with respect to this we are solving. Okay. So the first term minus the second term, we get KU1 minus KU2, right? Comma KU1 plus KU2. This is our first expression, okay? We found for KLKU, okay? Now for the KLU, right? KLU, right? We get, okay, so first let's solve for LU, right? LU, right, is equal to LU1, comma U2, okay? And this is equal to U1 minus B minus U2, right, comma U1 plus U2, okay? So KLU, right, becomes KU1 minus KU2, comma KU1 plus KU2, okay? So we can see that this is actually equal to this. Hence, this is actually a linear transformation, okay? Hence proof, okay? So we've seen that most of the formulas that we stated earlier can be used to show that an expression, okay, is a linear transformation. So we are actually going to call it a day, and in tomorrow's class, we are going to start with the more verse. I'm sorry for the technical issues today. I wasn't fluent enough. I'm so sorry. I'm having a bit of challenges with my tech today, and so I'm so sorry for that. I had to be referring. Okay, so let's pray and call it a day. Or we didn't pray before we started. Okay, I'm so sorry. But let's pray, okay, and let's call it a day. Father, we thank you for this opportunity to meet. We thank you for the ability to study. It's our prayer, O Lord, that you preside over our meeting as you study, O Lord. Grant us the understanding, okay. Grant us the understanding for us to study. And above all, O Lord, that you always be with us. That the Holy Spirit grant us retention memory and remember us all we've studied. In the name of Jesus, we pray with thanksgiving. Amen. So this all we've done, okay. If you have